Hello and welcome to episode 29 of Topcast. I didn't expect the introduction to go for as long, as I said at the end of the last one. So we're going to dive straight into the reading today with no introduction. Now, in the previous chapter, at the end of the previous chapter, David wrote, quote, "We are channels of information flow. So are histories, and so are all relatively autonomous objects within histories. But we sentient beings are extremely unusual channels along which sometimes knowledge grows." End quote. Okay, and so that's important because at the beginning of chapter 12, A Physicist's History of Bad Philosophy, with some comments on bad science, David writes in a conversation between himself and a reader. Okay, and the reader is asking David, the proverbial reader. The reader asks, "So I am an emergent, quasi-autonomous flow of information in the multiverse?" David, "You are." Okay, so let's have a short reflection on what quasi-autonomous flow of information in the multiverse means. So emergent, so not at the fundamental reductionistic level. So a person emerges from the laws of physics and from matter behaving in certain ways. We have emerged. We are complicated objects. We aren't fundamental, like an electron is fundamental, like a number is fundamental. People can have fundamental effects on the universe, but as he says there, we're emergent. Quasi-autonomous. Quasi meaning somewhat autonomous. So we are not entirely free. I'm not like Superman. I can't fly into the sky. I can't defy gravity. I obey the laws of physics. But given the laws of physics, there are choices before me. And my knowledge, the knowledge that I create, is the thing that determines the measure of universes in which a certain choice tends to have a higher measure compared to a lower measure. There are some places in the multiverse where I turn around and begin to do abstract art on the wall behind me. But Brett Hall is not the person that tends to do that kind of thing. There might be some sliver of universes where I just get bored with making YouTube videos about the work of David Deutsch, but they are, so far as I can tell, highly unlikely. Highly unlikely because I've never had any impulse to do abstract art before. If I started doing abstract art right now, that could possibly be explained by an aneurysm or something like that. In an extremely small measure of universes, that might occur. So I'm quasi-autonomous in creating knowledge about the things that I'm interested in, and usually only the things that I'm interested in. If the laws of physics do not rule it out, then yeah, it happens somewhere in the multiverse. But it's almost never in equal measure whenever there's a choice. There's a choice here between me doing what I'm doing now and any of an infinite number of other things. Now, in the overwhelming majority of universes, because I've preserved my personality over time for many, many years, I'm doing precisely this. And I will continue to do precisely this in the majority of universes. In some smaller number, I do something slightly different. And in some smaller number again, I do something even smaller again. The more and more different those things are to what my personality has historically been, the less likely and the smaller measure of universes in which that's going to occur. So I'm an emergent, quasi-autonomous flow of information in the multiverse, David says. Well, the reader says, but David says through the reader. And so that's what that means. And flow of information. So explaining how the multiverse itself evolves over time is more about the flow of information rather than, well, it increasingly will be more about the flow of information than it will be merely the movement of particles under the straightforward fundamental laws of physics. It will be better explained by the flow of information and the creation of knowledge over time. Now, at the beginning of this chapter, and I won't read this part, David has this fictional conversation with one of his readers. And the reader is summarizing what was going on in the last chapter and basically explaining how it is that we know the multiverse is the best explanation for what's going on in quantum theory. And so I'll just read the very last bit where David's talking about how the way in which we understand multiple universes exist is because of observations of photons. That's what's going on. We are noticing where photons of light are landing and where they're not landing. And the reader says, quote, "So that trickle of photons through the interferometer really does provide a window on a vast multiplicity of universes." And David says, in response, "Yes, it's another example of reach, just a small portion of the reach of quantum theory. The explanation of those experiments in isolation isn't as hard to vary as the full theory, but in regard to the existence of other universes, it's incontrovertible all the same." Reader, "And that's all there is to it?" David, "Yes." Reader, "But then why is it that only a small minority of quantum physicists agree?" David, "Bad philosophy." Reader, "What's that?" Okay, end quote. So here we're about to get into the discussion about bad philosophy. And David's just emphasising there that only a minority of quantum physicists agree. They don't do, so far as I know, surveys of professional physicists very often on what interpretation of quantum theory they prefer. But even the most recent ones do not show a majority of people endorsing the multiverse theory. Most are still either instrumentalists or believe in something like the Copenhagen interpretation, something like that. And this is what I was taught anyway in the 90s to 2000s with respect to quantum theory at the universities that I went through anyway. It was still the Copenhagen interpretation, or it was some form of there's no point asking, no one understands, or instrumentalism, of course. Just to be able to solve the problems. That's all that's important. That kind of thing. Okay, so getting back to the book, David writes, quote, "Quantum theory was discovered independently by two physicists who reached it from different directions, Werner Heisenberg and Erwin Schrödinger. The latter gave his name to the Schrödinger Equation, which is a way of expressing the quantum mechanical laws of motion. Both versions of the theory were formulated between 1925 and 1927, and both explained motion, especially within atoms, in new and astonishingly counterintuitive ways. Heisenberg's theory said that the physical variables of a particle do not have numerical values. Instead, they are matrices, large arrays of numbers which are related in complicated probabilistic ways to the outcomes of observations of those variables. With hindsight, we now know that multiplicity of information exists because a variable has different values for different instances of the object in the multiverse. But at the time, neither Heisenberg nor anyone else believed that his matrix-valued quantities literally described what Einstein called elements of reality. The Schrödinger equation, when applied to the case of an individual particle, described a wave moving through space. But Schrödinger soon realized that for two or more particles, it did not. It did not represent a wave with multiple crests, nor could it be resolved into two or more waves. Mathematically, it was a single wave in a higher dimensional space. With hindsight, we now know that such waves describe what proportion of the instances of each particle are in each region of space, and also the entanglement information among the particles. End quote. Okay, some exposition of that just on my behalf. Okay, so here's the Schrödinger equation, and the Schrödinger equation it's a wave equation, and that's at least one form of it. There's the time-dependent and the time-independent Schrödinger equation. We don't need to go into the details right now, but this one's the time-dependent one, and it says that at some particular time, t, h gives information, the h is the Hamiltonian, gives information about the energy of a particle which can take many values simultaneously, and that's the psi, that Greek letter there. We can graph, for example, the position, let's say, for example, the position of some particle at some particular time. And we get a graph, a wave that evolves over time, in fact. Here's the Wikipedia animation of psi for that particle, right there. And so, roughly speaking, what we're seeing here is that the particle is in all these places all at once. Now, these graphs of waves, are analogous to a picture of a snapshot in time of where a particle might be. what the range of energies is that it might have, or its momentum and so on. It's not just a single point. Now, this is physics that is different to classical mechanics. In classical mechanics, at a certain point in time, a particle has a single numerical value for a particular physical quantity, like position or energy or momentum or velocity. That's the Schrödinger picture. Physicists have for a long time, and indeed had for a long time before quantum theory, been comfortable dealing with waves. So it was natural for them to interpret the Schrödinger wave equation. It's describing a wave moving through actual space. But as David just said there, it's kind of misleading. It's a wave in a higher dimensional space. And what that means is a wave across the multiverse, not a wave in a single universe. That's in one way of speaking anyway. So an observer in a universe doesn't see a wave moving through space. But another way of looking at quantum theory, as David has mentioned here, is what has come to be known as the Heisenberg picture, or matrix mechanics. And so matrices look like this kind of thing, and I've picked these ones deliberately. These ones are known as the Pauli matrices. And the Pauli matrices can be used to represent a number of different quantities, but in particular, they can be used to represent the spin of a particle. And the spin of a particle is analogous to its angular momentum. Now, in classical mechanics, if something is spinning, it's got a certain angular momentum, the rate at which it is spinning and the difficulty with which it might be hard to stop this object from spinning, and that will have a single value. But in quantum mechanics, the spin of a particle is a matrice. It's not a single value. And so even if you don't understand what a matrice is, and it's not important, what is important is that it's not just a single number. So the spin is not a single number. In particular, when it comes to something like an electron, it can have spin up or spin down, so we say, and experiments can be done showing that if you fire a particular electron through this apparatus, the Stern-Gulach experiment, then it will demonstrate having two different spins simultaneously over time. Now, returning to the book, I've got these two kind of pictures of reality to some extent. There's this Schrödinger idea of particles being governed by a wave equation, and so appear to have some sort of wave-like property, and that's Schrödinger's picture. And then Heisenberg's picture, which is that the physical quantities that tell you information about a given particle are not single valued. They have to be represented by a matrice in some way. So David writes, going back to the book, quote, "Although Schrödinger's and Heisenberg's theories seem to describe very dissimilar worlds, neither of which was easy to relate to existing conceptions of reality, it was soon discovered that if a certain rule of thumb was added to each theory, they would always make identical predictions. Moreover, these predictions turned out to be very successful. With hindsight, we can state the rule of thumb like this. Whenever a measurement is made, all the histories but one cease to exist. The surviving one is chosen at random, with the probability of each possible outcome being equal to the total measure of all the histories in which that outcome occurs. At that point, disaster struck. Instead of trying to improve and integrate those two powerful but slightly flawed explanatory theories and to explain why the rule of thumb worked, most of the theoretical physics community retreated rapidly and with remarkable docility into instrumentalism. If the predictions work, they reasoned, why worry about the explanation? So they tried to regard quantum theory as being nothing but a set of rules of thumb for predicting the observed outcomes of experiments, saying nothing else about reality. This move is still popular today and is known to its critics and even to some of its proponents as the shut up and calculate interpretation of quantum theory." Pause there, my reflection. Yes, so this idea, the rule of thumb, where all of the when a measurement happens, all of the histories but one cease to exist. Well, this seems absurd, doesn't it? That the theory itself is describing there must be multiple histories. There must be all these different ways in which the particle exists simultaneously, all these positions it occupies, all these different momentas it has, all these different energies it has. That really is what the theory is saying. And if we take our theory seriously as a description of reality, well, that's what reality is. Reality really is described by particles that are simultaneously in many different positions. But the rule of thumb says, when you make a measurement, when you do an experiment, you only ever observe the thing with one value. It's only ever in one place, or with one energy, or with one particular momentum. And so the rule of thumb says, well, although the theory said that all these different histories really existed, all these different variables existed simultaneously, the experiment shows you there's only one, and so the rule of thumb is all of them disappeared except for one. Well, that's absurd. That brings consciousness into physics in a very fundamental way. That your act of observation has destroyed the vast bulk of reality, of physical reality, which is an astonishing claim to make and should not have been made, but it was. And because it was just so unbelievable, then what the physicists have said is, well, let's just deny the reality of multiple histories altogether deny multiple histories, and just say, use the formalism, use the mathematical formula in order to make predictions of what's going to happen next. Probabilistic predictions of what's going to happen next. When what should have happened was accept the fact all the histories exist and continue to exist. And we only ever observe one of those realities at any given time. Okay, returning to the book, skipping just a little bit, and David writes, both versions, in other words, Schrödinger and Heisenberg's, both versions of quantum theory were clearly describing some sort of physical process that brought about the outcome of experiments. Physicists, both through professionalism and through natural curiosity, could hardly help wondering about that process. So that physical process that brought about the outcomes of experiments. Just me talking again. Remember what the instrumentalist type people, the shut up and calculate type people were saying, was that the only purpose of quantum theory was to enable you to predict the outcome of experiments. But there has to be a physical process that produces the outcome of the experiment after all. And so no wonder physicists, through professionalism and natural curiosity, could hardly help wondering about that process. What is this physical process? And David writes, but many of them tried not to think about it. Most of them went on to train their students not to. This countered the scientific tradition of criticism in regard to quantum theory. Let me define bad philosophy as philosophy that is not merely false, but actively prevents the growth of other knowledge. In this case, instrumentalism was acting to prevent the explanations in Schrödinger's and Heisenberg's theories from being improved or unified. The physicist Niels Bohr, another of the pioneers of quantum theory, then developed an interpretation of the theory, which later became known as the Copenhagen interpretation. It said that quantum theory, including the rule of thumb, was a complete description of reality. Bohr excused the various contradictions and gaps by using a combination of instrumentalism and studied ambiguity. He denied the possibility of speaking of phenomena as existing objectively. Pause there, my reflection. So Bohr denied the possibility of speaking of phenomena as existing objectively. Does that sound familiar? Now, this predates the French postmodernists, but it had a strong influence on philosophy and a bad influence on philosophy. Once the physicists, the hard-nosed physicists, the supposed refinement of intellectual excellence that was physics, once the practitioners there start denying the existence of objective reality, we've got problems, because those people were respected. Einstein was one of the most famous people of the early 20th century. He was revered and respected. His colleagues, therefore, also were showered in a similar sort of respect and reverence, especially among the rest of the intellectual community and the academic community. So if one of their own, one of the great physicists, and physicists were, of course, respected and trusted and well-liked and revered because the amazing things they predicted worked. The amazing thing they predicted worked. They predicted theories of rocketry and the rockets worked. They predicted theories about ever better bombs and the bombs worked. They predicted theories about nuclear reactors and nuclear reactors worked, etc., etc., etc. What they said seemed to carry with it a weight because of how their theories worked. Now, despite the fact the epistemology there is all wrong, nonetheless, we have this culture of reverence for the words of physicists in particular. And physicists can sometimes be regarded as the new priests. And so unfortunately, if the priests start saying things like objective reality might not exist, we have a real problem. We have a deeper problem than merely false science or false claims, because we have the beginnings of a bad philosophy. If we deny the existence of objectivity and of objective reality, then we've got nothing to argue over. We've got no reason to debate, and debate is all about something that isn't solid. And we can never arrive at true answers if there's nothing true to argue about. Okay, let's go back to the book. David wrote of Niels Bohr, quote, "He denied the possibility of speaking of phenomena as existing objectively, but said that only the outcomes of experiments should count as phenomena. He also said that, although observation has no access to the real essence of phenomena, it does reveal relationships between them, and that, in addition, quantum theory blurs the distinction between observer and observed." Once again, end quote. Let's just reflect on that for a moment. So it blurs the distinction, according to Bohr, between observer and observed. That might also sound familiar to some people. It's a somewhat Buddhist notion. Now, Buddhism may certainly have truth within it, especially when it comes to studying the subjectivity of the mind, studying one's own mind, introspecting, etc. That aside, that the useful content of Buddhism is not encapsulated by this claim that there is a blurring in this sense between the observer and the observed. Despite this, it's this kind of thing which has been grabbed onto by mystics of all stripes and New Age type people as cashing out their own spurious claims, because the pioneers of quantum theory, struggling to understand this, said some very unfortunate things. But they were just the pioneers. They didn't understand quantum theory well enough, and so they were apt at saying sometimes ridiculous things, especially in the case of Bohr. Let's go back to the book. And David writes, quote, "As for what would happen if one observer performed a quantum level observation on another, he, Bohr, avoided the issue, which became known as the paradox of Wigner's friend after the physicist Eugene Wigner. In regard to the unobserved processes between observations, where both Schrödinger's and Heisenberg's theories seem to be describing a multiplicity of histories happening at once, Bohr proposed a new fundamental principle of nature, the principle of complementarity. It is said that accounts of phenomena could only be stated in classical language, meaning that language that assigned single values to physical variables at any one time. But classical language could be used only in regard to some variables, including those that had just been measured. One was not permitted to ask what values the other variables had. Thus, for instance, in response to the question, which path did the photon take in the Mach-Zehnder interferometer, the reply would be that there is no such thing as which path when the path is not observed. In response to the question, then how does the photon know which way to turn at the final mirror, since this depends on what happened on both paths, the reply would be an equivocation called particle-wave duality. The photon is both an extended, non-zero volume, and localized, zero volume object at the same time, and one can choose to observe either attribute but not both. Pause there, my reflection. Yes, this is standard stuff in textbooks. The typical physics textbook, high school, undergraduate level, when introducing quantum theory to people, generally falls back onto particle-wave duality stuff. And this is in fact what the majority of science popularizers today continue to regurgitate. And so it sounds plausible and attractive that because it seems as though, given classical type experiments, where there are certain observations we can make in quantum theory that seem to show that particles like electrons really do act like particles some of the time. They can collide into things. They can bounce off things. This is what particles do. They carry momentum with them. That this is evidence for their particle type nature. But there are other experiments you can do, interference experiments, passing single electrons through narrow slits, and we can then observe interference effects. And these interference effects are proof positive, so it's said, of a wave type nature. And so therefore we just say electrons are waves and particles at the same time. To some people that's satisfactory, especially when you're introduced to this for the first time and everything else is really complicated and difficult to understand. Well, being waved away with, oh, it's a wave and a particle at the same time, can shut some people up. But of course, if you understand what David's just said there, that an object like a photon or an electron or any other particle is sometimes, not sometimes, it is simultaneously of near zero volume, it's a particle, localized, and extended throughout all of space, non-zero volume thing, simultaneously. Well, this violates logic. But of course, some of the early pioneers of quantum theory and even people today will say, well, there's something deeper than logic, which is quantum theory. And so you need a new kind of logic to understand what's going on. Now that's a violation of reason. If the law of the excluded middle is something we should want to preserve. Something can't both be X and not X at the same time. Either here, I am here now, delivering another episode of Talkcast, or I'm not. I'm not simultaneously doing both. You might say, well, in the multiverse, I'm somewhere else. No, here right now, in this universe, speaking to you. Either it's me here speaking to you right now, or this is not happening. It's one or the other. I'm not both here doing this and not doing this at the same time. But in quantum theory, some people want to say that that, in fact, is what's going on. That particles are both in one place and in many places at the same time. Okay, returning to the book, and David writes, quote, often this is expressed, this concept of the extended through space and localized at one point, is expressed in the saying, it is both a wave and a particle simultaneously. Ironically, there is a sense in which those words are precisely true. In that experiment, the entire multiversal photon is indeed an extended object, a wave. So across the multiverse we have this, and this has been explained in my previous videos. So the wave is extended through the multiverse, while instances of it, particles in histories, are localized. Unfortunately, that is not what is meant in the Copenhagen interpretation. There, the idea is that quantum physics defies the very foundations of reason. Particles have mutually exclusive attributes, period. And it dismisses criticisms of the idea as invalid because they constitute attempts to use classical language outside its proper domain, namely describing the outcome of experiments. Okay, now I'm skipping a little bit, back to the book, and David writes, for decades, various versions of all that, all this vagueness with respect to quantum theory, were taught as fact. The anthropocentrism, the instrumentalism, and all in university physics courses, and even today, I should say. Few physicists claimed to understand it. None did. And so students' questions were met with such nonsense as, if you think you've understood quantum mechanics, then you don't. Inconsistency was defended as complementarity or duality. Parochialism was hailed as philosophical sophistication. Thus, the theory claimed to stand outside the jurisdiction of normal, i.e. all, modes of criticism, a hallmark of bad philosophy. Its combination of vagueness, immunity from criticism, and the prestige and perceived authority of fundamental physics opened the door to countless systems of pseudoscience and quackery, supposedly based on quantum theory. Its disparagement of plain criticism and reason has been classical and therefore illegitimate, has given endless comfort to those who want to defy reason and embrace any number of irrational modes of thought. Thus, quantum theory, the deepest discovery of the physical sciences, has acquired a reputation for endorsing practically every mystical and occult doctrine ever proposed. End quote. Well, that's a brilliant David Deutsch passage there. And it just sums up in a very forceful way how quantum theory, this amazing pinnacle of human intellectual endeavour, the truth of quantum theory, what quantum theory has allowed us to achieve as a species, new technologies, new ways of understanding reality. Ironically, because of the way it began, with vagueness and the immunity from criticism that some of the practitioners couch these ideas in, has caused quantum theory to, in the minds of some people, justify all manner of weird stuff. And so New Age type people, certain kind of Buddhist thinkers, quacks of various kinds, cranks of various kinds, dishonest interlocutors, and as we will see, certain kinds of philosophers point to quantum theory as a justification for their own nonsense. That in some way, because of the language used by the pioneers of quantum theory, the unfortunate language, the unfortunate vagueness, that therefore their crazy claims are cashed out in some way by the crazy claims of the pioneers of quantum theory. But the crazy claims of the pioneers of quantum theory, or the bad claims of the pioneers of quantum theory, were made for, in many ways, honest reasons. They were honestly trying to find the truth. And people today who use and point to quantum theory are oftentimes being quite dishonest. Dishonestly repurposing errors made in the past and presenting them as fact, and they're not fact. Admittedly, some of these people are innocently simply ignorant, but a lot aren't, a lot are not. All right, back to the book. David writes, not every physicist accepted the Copenhagen interpretation or its descendants. Einstein never did. The physicist David Bohm struggled to construct an alternative that was compatible with realism and produced a rather complicated theory, which I regard as the multiverse theory in heavy disguise, though he was strongly opposed to thinking of it in that way. And in Dublin in 1952, Schrdinger gave a lecture in which at one point he jocularly warned his audience that what he was about to say might seem lunatic. It was that when his equation seems to be describing several different histories, they are not alternatives, but really happen simultaneously. I'll say that again. When his equation seems to be describing several different histories, they are not alternatives, but all really happen simultaneously. This is the earliest known reference to the multiverse. Here was an eminent physicist, joking that he might be considered mad. Why? For claiming that his own equation, the very one for which he had won the Nobel Prize, might be true. End quote. That's another brilliant David Deutsch, very brief paragraph there, talking about Schrödinger. So Schrödinger, one of the discoverers of quantum theory, early pioneers, 1930s, has said that his own equation that explains what's going on with subatomic particles, he said that these equations describe particles with many different histories simultaneously, that occupy many different positions simultaneously. And that these alternatives really do happen, he said. And then David writes that he was joking that he might be considered mad. Why? For claiming that his own equation, the very one for which he had won the Nobel Prize, might be true. Okay, back to the book. David writes, Schrödinger never published that lecture and seems never to have taken the idea further. 5 years later, and independently, the physicist Hugh Everett published a comprehensive theory of the multiverse, now known as the Everett interpretation of quantum theory. It took several more decades before Everett's work was even noticed by more than a handful of physicists. Even now that it has become well known, it is endorsed by only a small minority. I've often been asked to explain this unusual phenomenon. Unfortunately, I know of no entirely satisfactory explanation. But to understand why it is, perhaps not quite as bizarre and isolated an event as it may appear, one has to consider the broader context of bad philosophy. Error is the normal state of our knowledge and is no disgrace. There's nothing bad about false philosophy. Problems are inevitable, but they can be solved by imaginative, critical thought that seeks good explanations. That is good philosophy and good science, both of which have always existed in some measure. For instance, children have always learned language by making, criticizing and testing conjectures about the connection between words and reality. They could not possibly learn it in any other way, as I shall explain in chapter 16. Bad philosophy has always existed too. For instance, children have always been told, because I say so. Although it is not always intended as a philosophical position, it is worth analysing it as one. For in 4 simple words, it contains remarkably many themes of false and bad philosophy. First, it is a perfect example of a bad explanation. It could be used to explain anything. Second, one way it achieves its status is by addressing only the form of the question and not the substance. It is about who said something, not what they said. That is the opposite of truth-seeking. Third, it reinterprets a request for a true explanation, why should something or other be as it is, as a request for a justification. What entitled you to assert that it is so? Which is the justified true belief chimera. Fourth, it confuses the non-existent authority for ideas with human authority, power, a much-travelled path in bad political philosophy. And fifth, it claims by this means to stand outside the jurisdiction of normal criticism. Okay, and I'm just skipping a little bit where David writes about empiricism. Empiricism is a false philosophy, but it at least allowed progress to continue. But then empiricism got taken too literally, and it became positivism. And positivism was about eliminating from science anything that could not be derived from observations. But still this didn't cause, this still wasn't really bad philosophy. This wasn't bad philosophy, this was just merely false philosophy because progress was still able to continue. And I might just go through David's little anecdote here about Ernst Mach, where he writes, quote, "For instance, the physicist Ernst Mach, father of Ludwig Mach of the Mach-Zehnder interferometer, was also a positive philosopher, influenced by Einstein, spurring him to eliminate untested assumptions from physics, including Newton's assumption that time flows at the same rate for all observers. That happened to be an excellent idea, but Mach's positivism also caused him to oppose the resulting theory of relativity, essentially because it claimed that space-time really exists, even though it can't be directly observed. Mach also resolutely denied the existence of atoms, because they were too small to observe. We laugh at this silliness now, because we have microscopes that can see atoms, but the role of philosophy should have been to laugh at it then." I'm skipping a little bit. David mentions that Einstein rejected positivism because he was a realist, and so Einstein never accepted the Copenhagen interpretation. And David wonders out loud, if Einstein took positivism more seriously, would he perhaps have included that space-time, that thing that general relativity forced us to endorse the reality of, would he himself has dismissed the idea of as space-time really existing? Okay, so David describes the leap from positivism, this idea that only that which can be derived from observations should be considered meaningful in science. And this led to a denial of physical reality in general. Thomas Kuhn, and David wrote of Thomas Kuhn, quote, "Thomas Kuhn wrote, quote, 'There is a step which many philosophers of science wish to take and which I refuse. They wish, that is, to compare scientific theories as representations of nature, as statements about what is really out there.'" End quote of Kuhn. David continues, "Positivism degenerated into logical positivism, which held that statements not verifiable by observation are not only worthless, but meaningless. This doctrine threatened to sweep away not only explanatory scientific knowledge, but the whole of philosophy. In particular, logical positivism itself is a political theory, and it cannot be verified by observation. Hence it asserts its own meaninglessness, as well as that of all other philosophy. The logical positivists tried to rescue their theory from that implication, for instance by calling it logical, as distinct from philosophical, but in vain. Then Wittgenstein embraced the implication and declared all of philosophy, including his own, to be meaningless. He advocated remaining silent about philosophical problems, and although he never attempted to live up to that aspiration, he was hailed by many as one of the greatest geniuses of the 20th century." End quote, my reflection. Even today, having gone through philosophy myself, Wittgenstein was absolutely regarded as the preeminent genius by even my favourite lecturers. Now, I never really understood. I think he has a few quotes. It depends upon the way in which you read him. And Wittgenstein contradicted himself. There's the so-called early Wittgenstein and the late Wittgenstein. His way of speaking about philosophy has entered the philosophical tradition in many places. For instance, people talk about word games. Whenever you hear this term word games, that's from Wittgenstein. Wittgenstein thought that one function of language was to communicate, but what we are doing as people is we're playing word games with one another. And so when scientists are talking, they're engaged in a certain kind of word game, which is very different to what a parent and a child might engage in, or a patient and a doctor might engage in. So, yes, this was Wittgenstein's view, the later Wittgenstein. The earlier Wittgenstein, who wrote Tractatus Philosophicus, believed that language served the function of simply describing physical reality and that's it. And of course, only that which could be observed was worthy of being a part of science and rational discourse. And I think I've mentioned before that Wittgenstein had this view of his own philosophy as being like a ladder which one uses to climb out of a well. And once you've used the ladder to climb out of the well, you can discard the ladder as well. And so that's what he thought of his own philosophy. And at the end of the Tractatus, he has that famous line, "Whereof one cannot speak, thereof one should be silent," or "thereof one must be silent." Now, on the one hand, it could be the case that it's as strong as, that what that means is that we should be silent about all philosophical problems. And of course, that's ridiculous. That closes off knowledge progress in many, many areas, because we need progress in philosophy. And this is one of the great debates between Karl Popper and Ludwig Wittgenstein. They didn't get on particularly well, but Popper took his ideas seriously and criticised them in many places. You can go back through my podcasts, or my talkcasts, and there is an audio version of me describing Mr. Popper's problems. I think that's the title of it. And about some of the great debates between Popper and Wittgenstein. But this quote, Wittgenstein's at the end of the Tractatus, "Whereof one cannot speak, thereof one must be silent," also has this other meaning. Like I say, people have different readings of Wittgenstein because he was so vague, which isn't a good quality, right? It's kind of theology. But philosophers love this. They love referring to the original texts and trying to grapple with what did he really mean. But one reading of that quote is, for him not to be in a position of dismissing metaphysics, certain parts of philosophy, but him simply saying that although there is this reality beyond which we don't have a way of speaking, it's real, but it transcends the ability of language to capture. And so, he wouldn't necessarily reject something like belief in God. He would simply say, well, it might very well be real, but there's no point engaging in debate about it. There's no point getting upset and fighting about it, because we don't have the language to capture it. It transcends human intellect. Now, this is not a position I hold. I am a universalist with respect to the mind, and so I think there is nothing that can't be understood if we simply put our minds to it, if we're interested enough to tackle that idea, tackle that problem. But Wittgenstein's position on that is at least interesting. And it kind of leads into some other linguist philosophers. The Sapir-Wharf hypothesis is what I'm thinking of. And these guys basically say that language is like a set of blinkers that you put on, and it constrains the way in which you can possibly think about the world. And it's in that same tradition of language is everything. And so philosophy today, very much even in the analytic tradition, we have on the one hand the continental and postmodernist type tradition, and we have the analytic tradition. The analytic tradition is still very much centered on linguistics and language, and David's about to get into that. And so let's just go back to that. And David writes, quote, "One might have thought that this would be the nadir of philosophical thinking, but unfortunately there were greater depths to plumb. During the second half of the 20th century, mainstream philosophy lost contact with and interest in trying to understand science as it was actually being done, or how it should be done. Following Wittgenstein, the predominant school of philosophy for a while was linguistic philosophy, whose defining tenet was that what seem to be philosophical problems are actually just puzzles about how words are used in everyday life, and that philosophers can meaningfully study only that. Next, in a related trend that originated in the European Enlightenment but spread all over the West, many philosophers moved away from trying to understand anything. They actively attacked the idea, not only of explanation and reality, but of truth and reason. Merely to criticize such attacks for being self-contradictory, like logical positivism, which they were, is to give them far too much credence. For at least the logical positivists and Wittgenstein were interested in making a distinction between what does and does not make sense, albeit that they advocated a hopelessly wrong one. One currently influential philosophical movement goes under various names, such as postmodernism, deconstructionism, and structuralism. Depending upon historical details that are unimportant here, it claims that because all ideas, including scientific theories, are conjectural and impossible to justify, they are essentially arbitrary. They are no more than stories, known in this context as narratives. Mixing extreme cultural relativism with other forms of anti-realism, it regards objective truth and falsity, as well as reality and knowledge of reality, as mere conventional forms of words that stand for an ideas being endorsed by a designated group of people, such as an elite or consensus, or by a fashion or other arbitrary authority. And it regards science and the Enlightenment as no more than one such fashion, and the objective knowledge claimed by science as an arrogant cultural conceit. Perhaps inevitably, these charges are true of postmodernism itself. I'm just inserting my own commentary here, and the cultural Marxism that exists now, the grievance study stuff that I've been talking about, where this has become even more pronounced. Okay, so I'll just go back and reread this section. David writes, quote, "Perhaps inevitably, these charges are true of postmodernism itself. It is a narrative that resists rational criticism or improvement, precisely because it rejects all criticism as mere narrative. Creating a successful postmodernist theory is indeed purely a matter of meeting the criteria of the postmodernist community, which have evolved to be complex, exclusive, and authority-based. Nothing like that is true of rational ways of thinking. Creating a good explanation is hard, not because of what anyone has decided, but because there is an objective reality that does not meet anyone's prior expectations, including those of authorities. The creators of bad explanations, such as myths, are indeed just making things up. But the method of seeking good explanations creates an engagement with reality, not only in science, but in good philosophy too, which is why it works, and why it is the antithesis of concocting stories to meet made-up criteria. Although there have been signs of improvement since the late 20th century, one legacy of empiricism that continues to cause confusion and that has opened the door to a great deal of bad philosophy is the idea that it is possible to split a scientific theory into its predictive rules of thumb on the one hand and its assertions about reality, sometimes known as its interpretation, on the other. This does not make sense because, as with conjuring tricks, without an explanation, it is impossible to recognize the circumstances under which a rule of thumb is supposed to apply. And it especially does not make sense in fundamental physics because the predicted outcome of an observation is itself an unobserved physical process. Pause there, my reflection. And again, this whole idea of logical positivism and various other kinds of philosophy that assert that we cannot make meaningful statements about that which are unobserved, those things that are unobserved, would completely dismiss the vast bulk of science. Almost everything interesting in science is something we cannot observe. The evolution of species over time. David's favourite example of dinosaurs. No one's going to observe a dinosaur. We're only going to observe fossils. The Big Bang. No one's going to observe the Big Bang. We observe things going on 13.5 billion years afterwards. Fusion in the core of stars. Subatomic particles smaller than protons, quarks and things, I don't know, maybe we can see quarks. Neutrinos, planets that we have not yet observed, orbiting stars that we cannot yet see. There is a whole bunch of things that we can't observe, but which we know must be real, given our best explanations, given what we know about reality. Okay, in the next bit, David goes through the dinosaur interpretation of fossils that I just mentioned. And I've mentioned this many times over the Beginning of Infinity series, so I won't go through it all there, but certainly worth reading there in chapter 12. So I'm skipping those few pages, and instead we'll go to the section on psychology, which has had a lot of influence actually, I think, in the intellectual community ever since the Beginning of Infinity was published. In fact, it was only a couple of days ago. I myself received a paper from some psychologists working at the University of New South Wales, my old alma mater, specifically talking about how Deutsch's work in the Beginning of Infinity and elsewhere had influenced their own thinking about psychology, and they were psychologists. So let's read what David writes about this. Let me give an example from a distant field, psychology. I have mentioned behaviorism, which is instrumentalism applied to psychology. It became the prevailing interpretation in that field for several decades, and although it is now largely repudiated, research in psychology continues to downplay explanation in favour of stimulus-response rules of thumb. Thus, for instance, it is considered good science to conduct behavioristic experiments to measure the extent to which a human psychological state, such as, say, loneliness or happiness, is genetically coded, like eye colour, or not, such as date of birth. Now, there are some fundamental problems with such a study from an explanatory point of view. First, how can we measure whether different people's ratings of their own psychological state are commensurable? That is to say, some proportion of people claiming to have happiness level 8 might be quite unhappy, but also pessimistic that they cannot imagine anything better. So let's pause there in my reflection. So just to hammer that home a little bit, two people could have exactly the same psychological state. And if you ask them, you ask of, let's say you've got John and Joe, and John and Joe are sitting there and they both in objective reality have the same psychological state. And you ask them both, on a scale of 1 to 10, 10 being the highest, how happy are you? John might very well say 8, and Joe might very well say 6. They don't have the same standards. We don't know what the knowledge is that they've got in their mind about how they should be feeling at any particular point. Okay, so that's a serious problem. That epistemology, knowledge about knowledge, is going to affect their ratings of their own subjective experience. But this is what psychology sometimes attempts to do. It attempts to try to get at a person's inner mind by asking them questions and having them do surveys, assessing the contents of their own mind. But how objective are they? How accurate are they? Or how commensurate is it that their assessment is going to agree with the assessment of someone else, that their standards are going to be the same as someone else's? No answer, of course. Right? So just continuing. David writes, quote, "And in some of the people who claim only level 3 might in fact be happier than most, but have succumbed to a craze that promises extreme future happiness to those who can learn to chant in a certain way. And second, if we were to find that people with a particular gene tend to rate themselves happier than people without it, how can we tell whether the gene is coding for happiness? Perhaps it is coding for less reluctance to quantify one's happiness. Perhaps the gene in question does not affect the brain at all, but only how a person looks. And perhaps better looking people are happier on average because they are treated better by others. There is an infinity of possible explanations, but the study is not seeking explanations. It would make no difference if the experimenters tried to eliminate the subjective self-assessment and instead observed only happy and unhappy behaviour, such as facial expressions, or how often a person whistles a happy tune. The connection with happiness would still involve comparing subjective interpretations, which there is no way of calibrating, to a common standard. Say that again. The connection with happiness would still involve comparing subjective interpretations, which there is no way of calibrating to a common standard. But in addition, there would be an extra level of interpretation. Some people believe that behaving in happy ways is a remedy for happiness. So for those people, such behaviours might be a proxy for unhappiness. Pause there, my reflection. So just notice that. This is a theory in this positive psychology movement, that you can behave your way to happiness. So if you feel unhappy, then you should pretend to be happy, and eventually you will be more and more happy. You should smile more often. You should regard yourself as being happy even if you don't feel happy, and eventually that will be its own reward. And so that's a problem for studies like this as well. And David goes on, quote, "For these reasons, no behavioural study can detect whether happiness is inborn or not. Science simply cannot resolve that issue until we have explanatory theories about what objective attributes people are referring to when they speak of their happiness, and also about what physical chain of events connects genes to those attributes." So how does explanation-free science address the issue? First, one explains that one is not measuring happiness directly, but only a proxy, such as the behaviour of marking checkboxes on a scale called happiness. All scientific measurements use chains of proxies, but as I explained in chapters 2 and 3, each link in the chain is an additional source of error, and we can avoid fooling ourselves only by criticising the theory of each link, which is impossible, unless an explanatory theory links the proxies to the quantities of interest. That is why, in genuine science, one can claim to have measured a quantity only when one has an explanatory theory of how and why the measurement procedure should reveal its value and with what accuracy. Pause there. I'll end this episode here, but that's an important point there to end on. The explanatory theory itself will tell you what quantities can be measured. And also, as David says elsewhere, a physical quantity quoted without uncertainty is strictly meaningless. So if someone just said, you could just say, my weight is 65 kilograms. Well, to a physicist, one wants to know on what kind of scale that has been measured. You know, is it 65.0? Is it 65.00001? Is it 64.9? The scale would give these could give this sort of information. So if you just say 65, well, that doesn't really tell us much at all. So we've got some more left to go with this chapter. So it'll be episode 3 for chapter 12, and we'll finish this in the next episode of Topcast. Once more, thank you to people who are supporting me on Patreon. I think I'm getting close to 10 Patreons right now, but thank you so much to everyone who is. It means a lot, and it's certainly helping me continue with this series, which has many more episodes to go. But until the next episode, see you later.